So today we are going to be talking about intuitive performance. So this is the lazy approach to algorithm optimization. First, a small disclaimer. I won't explain all the details. If you don't get them, that's fine, and just follow the big ideas. And you can, of course, ask me later in the performance Slack group if you have any questions. So why lazy? I like ideas that are easy to explain and get you tremendous kind of benefit from. So ideally, the idea would be explainable in 30 minutes. So effectively 20% effort for 80% effect. Of course, if you're optimizing things and you want to go past the 80% line, then you may need to do other things than I've explained here. However, the principles have served me well over the time. So the basic process for optimization. This is the general outline. First, you always measure things. It helps you guide your decisions. So always measure first. I won't cover this time. Then you make a few hypotheses. How do you make it fast? And then you try to figure out solutions to those. Like, why was it that slow? Why did it take that much time? And then you try them and measure again and then keep the best solution, if there is one. And just in case, keep the second best solution around as well. And rinse and repeat. Today, I'm going to be focusing on how to make these hypotheses and with as little effort as possible. And I'm going to show a few examples as well to illustrate my ideas. So 5% heuristic. It's approximately 5%. It could be 10% or 2% depending on the situation, but let's say 5% for this presentation. If something is more than 5%, then try reducing. It seems obvious, but it might be not obvious where you want to apply it. So I'm going to be covering these places where you might apply this 5% heuristic. The big picture. First, the big picture. If something is taking less than 5%, then something else is taking more than 5%, then you need to focus on the thing that takes more than 5%. It's obvious. Like you start from the things that have the biggest benefit. But it's also the other way around. If something is less than 5%, then usually the performance improvements you get require more effort than the things that are big on your, after measuring the either memory usage or performance, whatever metrics you use. So, as our first example, base 58 encoding. If you haven't recently done any encoding, let's walk through a simple base 10 example. So you divide by 10 and get the remainder and main part, and then you repeat it multiple times to get this number 1, 2, 3 on the right. That should kind of give a short reminder. In practice, the code roughly looks like something like this. But of course, real code is messier. To encode base 58, we need to encode arbitrarily sized data. So first, here we will use big integer to contain the large number and then divide it by the base 58. This is one of the cases where I measured that, the performance here was pretty bad. Of course, this ended up in my slowest numbers. One of my first thoughts was to convert by blocks. So I divide the input into right-sized chunks and then apply the conversion magic. However, I realized that I needed 128 bytes sized blocks, and that didn't seem quite nice. So I would have needed to implement 1024, but yeah, too much effort. This is the lazy version. But one of the things about lazy approaches, you don't have to implement the perfect solution. You can try to reduce it to the 5% some other ways, kind of taking shortcuts as you need to. One of the ideas is that when you take 58 to the power of 10 and then take the modulus of that with 58, then it's going to be the same number. And this power of 10 nicely fits into an integer. So, for example, with base 10, I might first divide by 100 this big integer number, and then later do the small iterations in a loop. So basically, I'm first converting to base 58 to the power of 10, and later converting to the base 58. And of course, real code looks messier, and as a result, I got it 10 times faster. By making this hotspot into two different parts, one which made it much, much faster. Next part, communication. If you're communicating over some medium, then it should take less than 5% compared to the work being done. As an example, when is it useful to start a new worker? You might kind of start guessing like, oh, I need to do this much work and so on, but like this is the lazy approach. We need to be quicker with decisions. So roughly speaking, channel send is about 150 nanoseconds. So we can calculate what would it need to be, what would I need to make it 3000 nanoseconds, or make it 5% of the overall time. So that's 3000 nanoseconds. And you can be safer and increase it by 2, so 6000 nanoseconds. So workers that communicate over channel, yeah, make them 6000 nanoseconds at least. If they are less than that, maybe don't use coroutines in the first place. And this applies in different scenarios. So SQL calls, GPO calls, and a bunch of other situations. And if you can just measure the communication overhead, and then you know how much work you need to patch together to make it efficient. Predictability. So there's this idea that branch misprediction and call mispredictions end up slowing down your CPU, because if you do predictable things, then CPU will immensely help you. The usual example, let's take a list of random integers and then sum them based on some condition. So when it's less than 50, let's say. And I needed to do some tweaks so that compiler doesn't optimize too much to make that example work. So in the future, when the compiler is even better, it might be as fast as the previous without sorting, but the branch prediction still works. So if we compare these two, benchmarking how much does it take to sum the unordered and then the sorted numbers, then we can see that, oh, it's 69,000 nanoseconds. You could try to guess, but usually that guess is wrong. And for this case, it was 23,000 nanoseconds. And it goes the other way as well. If you have interfaces, here we have a shape where different shapes calculate areas. I know it's a facilitated example. And we calculate the total area. And similarly, we can take random shapes and try to calculate the area. When they are not ordered, it takes 88,000 nanoseconds. But we can also sort them by type. Don't look at the code. It's not for production use. But if you sort them by, let's say, circles first and then the rectangles, then you can improve the performance to 39,000 nanoseconds. So it ended up being 2 times faster by sorting the types. Of course, obviously, removing the branch or interface is even better, but that isn't in the spirit of being lazy. Computation closeness. You want those computations to be in a small region in memory, because if you are asking lots of things from the memory, it cannot reasonably cache them. So if you can ensure that most of your memory accesses are inside that 5 megabyte range, then it's going to be much faster because it's more likely to hit the cache. So, and there are a few approaches how to make this 5 megabyte data structure in your code. One is to use a cache, which is essentially keeping copies of some of the data such that most of the interaction is with that cache, essentially. And you don't need to consider too much which one to choose. You can use the least recently used or random replacement. They work pretty well for the first stage of performance improvements. And the other data structures are reductions, which is kind of like combining all the data set into fewer data points such that you don't have to always look at the large data, or you know exactly where to look in the large data structure. And there are a bunch of options there as well. So sorting your data is also a good way of improving this cache locality. For example, here is a graph traversal algorithm that sorts the graph nodes that it needs to iterate over before iterating. As a result, the memory accesses are faster because they are near each other in memory. In that scenario, that improved the whole performance of the algorithm by factor of 2. And of course, the sorting doesn't need to be perfect. If you can do some lazy, slow, or faster sorting that kind of sorts the items, then that will help with that as well. So, memory usage. You can also try reducing memory. If you use less memory, it's also more likely to fit into a cache. And you can also look for things that vary very little. For example, if you're dealing with only letters, then there usually is a more compact representation of a string that contains only ASCII letters. For example, this is a real world example. However, I have forgotten some of these details because it was 5 years ago or more. In principle, we had an ID that contained some letters and characters, total about 41, and it was 12 characters long. And I needed to reduce the in-memory usage so that the reporting engine worked faster. And the first idea was I can use a lookup table to do that. So just map the ID to some UINT64 and then kind of do this translation while you calculating the reporting. However, that ended up being slower because all of the map accesses ended up being slower than actually just using the longer ID. However, I had a thought, what if I encoded the character set into an integer, so kind of compacting the ID. However, by initial calculations, it would have needed 64.29 bits, which was so close to UINT64. And I was thinking, like, if there was one letter less in length, then it would have been fine, but I cannot really change the length. So I thought, but what if I didn't represent all the IDs, just part of them? Then I would be able to fit most of them. And I knew that some of the IDs are really rare. Most of them start with A to C. So I did this small change to it where I compacted anything that started with a letter and the rest of them put into the lookup table. And most of the times the lookup table stayed empty or contained maybe one or two items, which significantly reduced the memory usage and also improved the performance of the overall. Now, pointers are also kind of things to watch out for. If they take more than 5% of your memory in a data structure, then reduce them. As an example, linked list, one of those good starting examples, you can replace the value by multiple values. So you don't have to store a single value in the node, but multiple. Alternatively, you can also use some offset if you know that the values are small and there aren't going to be too many of those other nodes that you need to link to. Or better yet, sometimes replacing it with a slice will do magic on your data structure and improve the performance. And of course, there were different ways you can use those same ideas on graphs and trees, but I'm going to pick one of my examples is a tree, which is for looking up the words, essentially. We have this slow version of this node structure. So the idea would be, how can we make it faster? First, we notice that, there are these long linked lists there that we really don't like. So we can replace them with a single suffix. This is a common optimization, so nothing new here. However, we can start inspecting. Here we have a slice of nodes. It's going to have a pointer inside of it and going to point somewhere in the memory where we don't know. We might actually want to replace it with a number of edges and where the edge is inside the slice of nodes. Of course, it will make the code more complicated. However, we got rid of this slice there and got rid of the pointer. The other thing we might notice is that, this label takes a rune, which makes sense for strings. However, most strings are just ASCII. So let's replace it with a byte. We can always represent a rune with bytes, so there's no loss in fidelity. And we might now look at the suffix. That's a string. It also contains a pointer, and we don't like pointers. So let's replace it with a maximum length of some number of bytes. We need to find a good number for it, but that's just few experiments to figure it out. And finally, we can notice that, there's this term, a Boolean, which takes 8 bits, and 7 of them are always empty. And we don't like empty bits because they just use up more memory than they need to. So we could combine this term and h count into a single byte field into flags, reducing this whole data structure to this 8 bytes and without any pointers. A neat benefit from this is that it can be also memory mapped from disk. So it's also faster to load than some pointery data structure. As a result, I did some performance testing on sorted strings. It was like 200 nanoseconds per key. And for the compact version, it was 100 nanoseconds. If I hadn't done any optimization, it would have been also 200 nanoseconds. So there was a significant benefit. And also trees have some other nice benefits to them. So yay for optimization. And it didn't take too much time to figure this out based on these few principles of this 5% and noticing where you can change those. So as a summary, 5% heuristic, the big picture. If it's less than 5%, don't worry about it. That needs more effort than you want to use, I guess. Communication. Keep it less than 5% of the total work that you need to do. Predictability. If the misprediction is over 5%, try to reduce it somehow. If the computations aren't close in a 5 megabit range in most scenarios, then try to figure out whether there's a way to compact it into this 5 megabits. Memory usage. If you can, try to reduce it. It will generally help you. And if it's less than 5% of variance in the data structure values, then you can usually do some tricks to spatial gaze them and make them faster. And pointers, avoid them, use less of them, and it will be better. So 5% heuristic approximately. Not perfect, but useful enough. So thanks for listening, and I hope it helps you with your performance optimizations.